This is section 5.5 of your text, Applications of Inner Product Spaces. In the course that I teach, we are not going to cover the calculus methods of least squares approximations or Fourier approximations. So the only topic in 5.5 that I'm going to cover is the cross product. The cross product of two vectors in R3. The cross product of two vectors in R3 is a new vector in R3 that is orthogonal or perpendicular to both of the original vectors. So if we have two vectors in R3, to find the cross product, we're going to take u2v3 minus u3v2i minus u1v3 minus u3v1j plus u1v2 minus u2v1k. Now that's kind of difficult to try to remember because it's a formula, but we're very familiar with finding the determinant. And so we can remember that using the determinant form. So if I think about cofactor expansion on I, that gives me I times u2, u3, v2, v3, the determinant of that. And then minus, and then again, cofactor expansion, we're just using that first row. So I'm going to have u1, u3, v1, v3 multiplied by j. And then I'm going to have plus, and then using k, I've got u1, u2, v1, v2, k. And that is going to give me u cross v. So let's take a look at an example. In this example, we're going to find the cross product. I've rewritten the definition for finding the cross product. And we have the question where u is 2i plus 4j minus k, and v is negative I plus j plus 2k. So remember, if we want to find u cross v, the cross product of u and v, I'm going to think of this as I, j, k, and then I would have 2, 4, negative 1 from u, and then negative 1, 1, 2, negative 1, 1, 2 from v. So to find this, I'm going to do cofactor expansion on I. So I have 4, negative 1, 1, 2, I, minus, so there's a minus in front of the j, and then I'm going to have 2, negative 1, 2, cofactor expansion on that first row, and then plus 2, 4, negative 1, 1, k. So that gives me 4 times 2, which is 8, minus negative 1, so that's 9i, and then minus 4 minus 1, so 3j, and then plus 2 minus negative 4, so that's 2 plus 4, or 6k. So this is u cross v. This vector is a new vector in R3 that is orthogonal or perpendicular to my original two vectors of u and v. Let's now graph the vectors so that we can verify or just at least visually inspect that these are in fact orthogonal vectors. So our first vector u is 2i plus 4j minus k, that's graphed in red. And our second vector v, negative I plus j plus 2k, is graphed in blue. And the vector u cross v, the cross product of our vectors, 9i minus 3j plus 6k, is in green. So let's look at the green and the blue. And again, you can kind of see right there that that's going to be a 90-degree angle. That's orthogonal. And you can do the same with red and green. You can see just visual inspection Of course, we could mathematically verify as well, but we can see that this is an orthogonal vector. There are several properties of the cross product, and I'm going to let you go through those on your own. For the most part, they're very straightforward. The first set of properties are the algebraic properties of the cross product, and we're familiar with many of those from dealing with the determinant and other things that we have learned in this course. The second set of properties are the geometric properties. So U cross V is orthogonal to both U and V. The angle theta between U and V is found using the magnitude of U cross V, which is the magnitude of U times the magnitude of V times sine theta. U and V are parallel only if U cross V is equal to 0. And the parallelogram having U and V as adjacent sides has an area of the magnitude of U cross V, and we're going to use that one now in an example. Let's find the area of the parallelogram that has adjacent sides U and V. Again, the first step would be to find the cross product of U and V. So if we write this as the determinant of a matrix using I, J, and K in the first row, 1, 2, 1 in the second row, and -2, -1, 0 in the third row. -2, -1, 0. Then I am going to use, again, cofactor expansion. So 2, 1, -1, 0, I minus, and then 1, 1, -2, 0, J, again, just using cofactor expansion. That's where I got the 2, 1, -1, 0, and so forth. And then plus, and then I would have 1, 2, -2, -1, K. And that gives me 0 minus -1, so 1I, minus 0 minus -2, so 0 plus 2 is 2J. And then -1 minus -4 gives me plus 3K. So again, that's the cross product, but now I want to find the magnitude of the cross product. So the magnitude would be the square root of the coefficient squared. So that's 1 squared plus -2 squared plus 3 squared. And that gives me the square root of 1 plus 4 plus 9, or the square root of 14. The square root of 14 is the exact area of the parallelogram using those two vectors as sides. Coming up next is Chapter 6. 6.1 is an introduction to linear transformations.